Hi Rockridge, welcome to our third unit of the year. It's the first lesson of our new unit is solving absolute value equations and inequalities. So we're going to start off by doing this algebraically, and then a little later towards the end of the lesson we'll make some connections with the graphing, and then next lesson we'll dive deep into the graphing. So the majority of today will be algebra-based solving. So we first need to think of what the absolute value means. If you have the absolute value of something, that can be both the solution to that can be both the positive version of that something and the negative version of that something, right? So think of it this way. To solve this absolute value, the absolute value of x equals 3, to solve this we need to think, what numbers could x be? These numbers that have a distance away from 0 of a distance of 3. So what numbers on a number line, if you were to draw a number line, what numbers on a number line have a distance away from 0 equal to 3? And there are two things that have that, right? 1, 2, 3 up solves that, and 1, 2, 3 down solves that. So for these absolute values, we actually end up having two solutions, because what does absolute value mean? Absolute value means distance away from 0. That's what absolute value means. So the absolute value of x equal to 3 is solved by thinking, well gosh, a negative 3 is 3 away, and a positive 3 is 3 away from 0. And so therefore those are the two answers to this question. The way we solve absolute value equations algebraically is in 3 steps. The first step, and the most important, is to isolate the absolute value portion of the problem. Always do this first. Very, very important to isolate the absolute value portion first. Once that is done, or if you walk into a problem that already has that done, you need to set up two equations. The first equation equals the number that you started with. The other equation equals the opposite sign of that number. And then the third step is to solve each. So let me show you how this happens. So if you come upon absolute value of x equals 8, what was step number 1? Step number 1 was isolate the absolute value portion. We came upon this problem and the absolute value portion is already isolated. So step 1 was already done for us. Step 2 is to set up those two equations. So here's how we do that. The first equation is x equals the positive 8. And the second equation is x equals the negative 8, the negative version of the 8. Why is that? Well, we go back up to this little lesson. What numbers have a distance from 0 of 8? Positive 8 and negative 8. There's no more solving to be done. X is already by itself in both. So we have stated the answers to this particular absolute value equation. Now, we ramp it up a little bit on number 2. We should still check for a first step, isolating the absolute value portion. Number 2 already has the absolute value portion isolated, so we can go ahead and move to step 2. Let's set up two equations. 2x minus 3 equals the positive 7 we started with, and 2x minus 3 equals negative 7, the negative version of what we started with. Now we solve each. Add 3 to both sides, divide by 2. Add 3 to both sides, divide by, oh, sorry about that, got ahead of myself. Divide by 2. So add 3 to both sides, divide by 2. These two solutions are what we have for this absolute value equation. Absolute value equations have two answers. Let's look at example 3. Remember step 1, always isolate the absolute value portion. In number 3, it's not yet isolated. We have a little buddy here. We have negative 10 that's along with it. So we need to start by isolating the absolute value. In order to do that, we add 10 to both sides. We now have absolute value of x plus 1 equals 22. Now we can set up our two equations. Now that absolute value is isolated, we can set up our two equations. The first one is x plus 1 equals positive 22. The second one is x plus 1 equals negative 22. Please note, we did not break out x plus 1 from these bars of this absolute value jail. We can't break him out until we set up these two equations. Until this point, it's still sitting in the absolute value. Always remember, it stays in the absolute value until you've got it isolated and you're setting up your two different equations. Now we've broken out of absolute value jail. Now we solve each. Subtract 1 from both sides. So the two solutions to this, x is 21 and negative 23. Number 4, once again, we do not have an isolated absolute value. We must do that first. So let's do that now. In order to isolate it, we need to divide by negative 2 on both sides. We still have this 3x minus 1 inside this absolute value jail. You cannot break them out yet. Now, to break them out of that jail, we do our setup of our two equations. 3x minus 1 equals a positive 4. 3x minus 1 equals the negative 4. Both of these are our equations, so we solve each. 3x equals 5. X equals 5/3. 3x equals negative 3. X equals negative 1. Those are our two solutions to that absolute value equation. Number 5. We need to isolate the absolute value portion. The first thing we do for number 5 is multiply both sides by 2. To get rid of this 1/2, we have to multiply both sides by 2. So when I multiply this side by 2, I get 5 minus 3x in the absolute value, and I get negative 4 for the right-hand side. Now, let's pause and think for a moment. Absolute value. We know that when we take absolute value of things, we spit out positives, right? Look what's happening here. The absolute value of something equals negative 4. Can that ever happen? No, that can never ever happen. So because absolute value cannot produce negatives, there is no solution to this. So always look for that. Always look for absolute value of something equals a negative. You can pause and save yourself some work because there is no solution to this. There is no value of x you could ever put in here that would produce a negative number. Alright, so those are absolute value equations when there's an equal sign involved. Now we're going to talk about inequalities. Inequalities are solved similarly. They do have two parts to them, but it's a little different. We're thinking again, what numbers have a distance from 0 that is less than or equal to 3? That's what these inequalities mean. So instead of equals 3 and having two separate answers, we're going to have a range of values, right? We're going to have multiple values that solve this. So again, for inequalities, we still start with isolating the absolute value portion. That should always be done first. In order to break your stuff out of the absolute value jail, you need to set up two different inequalities. If you have a less than situation, you'll set up an and inequality. If you have a greater than inequality, you'll set up an or. After that, we'll solve each inequality. So let me show you what I mean by that. So example number 6. We're presented with the absolute value of x plus 5 is less than 4. So first of all, isolating the absolute value portion, that's already done for me. This is already isolated. The next step is to look and see if I have a less than or a greater than. Well, I have a less than. The absolute value is less than 4. So I need to set up a less than, I need to set up an and. And let me show you how that's done. X plus 5, I'm breaking it out of absolute value jail now, x plus 5 is less than 4 and greater than negative 4. Less thans are sandwiches, that's what I call them. X plus 5 is less than the 4 we had and greater than the negative version of the 4. At this point, I can solve each of these inequalities. I can solve them at the same time. Subtract 5 from all sections. So I'm left with x is less than negative 1 and greater than negative 9. Typically when we have these, we like to see them on a number line to see how they work out. So let's see how they work out. If x is less than negative 1 and greater than negative 9, what that looks like is between negative 1 and negative 9, everything in between would solve this inequality. You could put any number between negative 9 and negative 1 in for x, and you would spit out a 4. It's something less than 4. Something less than 4. So these inequalities will be a range of values. We started with a less than, and so we set up an and. Now number 7 is slightly different. First of all, we check to see if our absolute value portion is isolated. It is. It's all by itself here. Next, we check to see, do we have a less than or a greater than? This is the greater than symbol. Absolute value is greater than 4, and so we need to set up an or. Let me show you how that's done. We take the original, x plus 5 greater than 4, or x plus 5 less than negative 4. That's the setup. That's the two equation setup. That's how we break this out of the absolute value jail. It can't come out of here until we've set up two portions. Now we solve both sides. Subtract 5 from both sides. And this is your solution. Let's look and see what that looks like on a number line. Typically with these inequalities, we like to see number lines. So let's plot our negative 9 and our negative 1. Now let's see what happens here. X is greater than negative 1. What does that look like? X is greater than negative 1. Or it's less than negative 9. Less than negative 9. Notice we don't have a sandwich like we did in number 6. We don't have something sandwiched between two values. We have things going off in different directions. Ands, less than ands, look like this. Ors, greater than ors, look like this. Two things going off to the side. So that's a little self-check you can do to make sure your algebra was done correctly. Let's look at a couple more examples. Number 8. Remember, the first step should always be to isolate the absolute value. And this time we haven't been given that. We need to do some work here. So let's divide by 3 on both sides to make that happen. Absolute value of x minus 2 is greater than or equal to 2. Now it's isolated. I have not broken it out of absolute value jail yet. Remember, we can't do that until we set up our two-stepper. So right now, this is what I have. I've got absolute value isolated. Step 2, is this a less than or greater than? I've got absolute value of x minus 2 is greater than or equal to 2. So greater, that's an or setup. So my setup is x minus 2 greater than or equal to 2, or x minus 2 less than or equal to negative 2. That's my setup. And now, see, the absolute values get to go away. Solve each side. X is greater than or equal to 4. X is less than or equal to 0. That's my algebraic solution for that. Let's take a look and see what that looks like on a number line. Let's put a 0 here and a 4 here. And what are we expecting? greater than ors, we're expecting things to go off in two different directions, not be a sandwich. So let's see if that happens. X greater than or equal to 4, what does that look like? That looks like a solid circle, and greater than heads this way, so we're off to the right, we're off to a good start. Less than or equal to 0, solid circle on the 0, and we're saying everything less than 0. So we know we've done this right. A greater than or should be things going off in two different directions. Let's look at number 9. Do we have an isolated absolute value yet? Nope, no we do not. So number 9, we need to divide by 3 on both sides to isolate the absolute value. Now that we've done that, we can make our decision about less than or greater than. Well, we've got absolute value of something is less than or equal to 2. So we can go ahead and say, to break you out of absolute value jail, you are less than or equal to 2 and greater than or equal to negative 2. Less than and. To solve that, we add 2 to all sections. So we have x is less than or equal to 4 and greater than or equal to 0. The number line for this should look like a sandwich, right? Let's put a 0 here and a 4 here. We have solids because we have less than and equal to. And x is less than 4, so to the left of 4, and greater than 0, to the right of 0. So we've got any value between 0 and 4, including 0 and 4, will make this true. Our 10th example does not have the absolute value isolated again, so we have a first step of work to do. What do we need to do to isolate the absolute value? We need to add 1 to both sides. So now we have absolute value of 2x plus 4 is less than 10. Now we can make our decision. We have a less than, so that's an and. So to break this out of absolute value jail, we say 2x plus 4 is less than 10 and greater than negative 10. Now we can solve it. Subtract 4 from all sections. And then divide by 2 on all sections. So our less than and has produced another sandwich for us. So if we have a number line, we've got the number -7 and the number 3. We've got open circles because we are less thans, not less than equal tos. And everything less than 3 is over here, and everything greater than -7 is over here. So we've created the correct sandwich. Finally, number 11. Again, we don't have an isolated absolute value, and we actually have 2 steps of isolation that we're going to need to do here. Let's do the first step, subtract 1 from both sides. Let's continue isolating, divide by 2 on both sides. Notice that all through this isolation process, I bring my absolute value symbols with me the whole time. I can't break it out of absolute value until I do that 2-step setup. So until then, that absolute value is coming with me the whole time. Now, the absolute value portion is finally isolated. I can do my setup. What decision do I have to make? Let's see. I have absolute value of something is greater than the 12. So greater is or. Greater than is or. So I'm going to set up an or. I'm going to take 3x minus 9 is greater than the 12, or 3x minus 9 is less than the -12. Now I solve. Add 9 to both sides. Divide by 3. Add 9 to both sides. Divide by 3. Now I am expecting the or to look like things shooting off in two different directions on a number line. Let's check to make sure that happens. So let's put the -1 on there and the 7 and see what happens. X is greater than 7, so that looks like this. Or X is less than -1. That looks like this. So visually I can see that I've done this correctly. The or is shooting off in two directions, unlike the and that's sandwiched between two values. Alright, that's the majority of our algebra instruction for today. Let's switch and compare the algebra to the graphing that we've already talked about in previous units. Let's connect the algebra and the graphing. Remember how to graph y equals the absolute value of x plus 2 minus 3. Remember our HK format? And remember what generally an absolute value looks like on the graph? Well, let's check this out. This means I move left 2, down 3 to find the vertex of my absolute value, v. And since I have an invisible little positive 1 here, it means I go up 1 over 1, up 1 over 1, up 1 over 1 for this side of the v, and up 1, back 1, up 1, back 1, up 1, back 1 for that side of the v. So my absolute value function looks like this on the graph. So if that's my graph, where does the graph cross the x-axis? Let's pick that off visually. Well, I see that it crosses the x-axis here at positive 1, 0. And I see that it crosses the x-axis here at -1, 2, 3, 4, 5, -5, 0. Those are two places that the graph crosses the x-axis. On a number line, what number is 3 units to the right of -2? Let's plot a -2 here and go 1, 2, 3 units to the right of -2. This is -1, this is 0, this is 1. So 1 is 3 units to the right of -2. On a number line, what number is 3 units to the left of -2? 1, 2, 3. That goes -3, -4, -5 is 3 units to the left of -2. Notice what we've seen here. The points that we pulled off the graph that cross the x-axis, and moving to the right and to the left of -2 by 3 units, is producing our same solutions. So let's bring it all together here in the algebra. What numbers make the following equation true? Without even using what we did earlier, what numbers make this true? What can you add to 2 and then take the absolute value of and make a 3? Well, if you make x a 1, 1 plus 2 is 3. Absolute value of 3 is 3. If you make the x a -5, -5 plus 2 is -3. Absolute value of -3 is 3. So 1 and -5 make this equation true. Why does that matter? Well, let's look at our original here. Our original was y equals absolute value of x plus 2 minus 3. That was our original. Remember how when we had lines, how do we solve those? How do we see the x-intercepts of a line? What do we set equal to 0? We set y equal to 0 to see x-intercepts. So let's do that here. If we take this and set 0 equal to absolute value of x plus 2 minus 3, that turns, let's add 3 to both sides. We've got to isolate that. That's where we get this from, right? We set y equal to 0, and we solve that. So when we solve this, we got 1 and -5. So hopefully you've finally come to the conclusion after all of this work that the x-intercepts of an absolute value graph are the solutions to that absolute value algebra. X-intercepts and solutions are the same. Let's see that in a different way on the next connection. Now we have an upside down v, right? Remember when we have negatives out here, we make them upside down? So let's follow our HK format and go right 1, 2, 3, 4, and up 1, and make this an upside down graph. Down 1 over 1, down 1 over 1. Graph that. Where do we cross the x-axis? We cross it at 1, 2, 3, 0, and 1, 2, 3, 4, 5, 0. On a number line, what number is 1 unit to the left of 4? If I go left of 4, I'll get 3. What number is 1 unit to the right of 4? If I go right, I get 5. So we've got intercepts of 3 and 5. To the left and the right, we have 3 and 5. Remember how we got to this. What numbers can we put in here to make this a true statement? Well, if I was to put 5 in for x, 5 minus 4 is 1. Absolute value of 1 is 1. So 5 works. If I was to put 3 in here, 3 minus 4 is negative 1. Absolute value of negative 1 is 1. So 3 works. Where did this come from? Well, our original was y equal the negative absolute value of x minus 4 plus 1. If we set y equal to 0 to see the x-intercepts, it looks like 0 equals negative absolute value of x minus 4 plus 1. Subtract 1 from both sides. Divide by negative 1 on both sides. So this is where this thought process came from. Oh, I miswrote this here. Let's fix these signs here. Sorry about that. There we go. So by setting y equal to 0, we've got something that we can think about in this way and think, what are the two possible things that can make it true? So again, we've shown the x-intercepts of the graph, or the moving left and right on the number line, moving left and right on the number line, will help us reach the same conclusion that we do algebraically for these absolute value equations. Let's take a look at what we've got in number 3. Using what we learned from the last two examples, could we answer this without graphing it? Yeah, absolutely. If we want to find the solutions to this, or where they cross the x-axis, how do we find x-intercepts? We set y equal to 0. So now we've got a question. What can we put in for x that will make this true? What values of x minus 5, and taking the absolute value, will equal 9? Well, hopefully you quickly came to the conclusion if you put 14 in for x, 14 minus 5 is 9. Absolute value of 9 is 9. And we know we always have 2 of these, so what is the other thing we could put in here? Think about that for a minute. Hopefully you came up with negative 4. Negative 4 and negative 5 combined are negative 9. The absolute value of negative 9 is 9. So without graphing and just thinking about this problem, we can solve the solutions for this absolute value. How did you determine your answer? Well, just for a complete set of notes, we set y equal to 0. We know that finds the x-intercepts of any graph, lines, absolute values. The x-intercepts are the solutions. And for future reference, the solutions are also known as the roots. So let's solve the equation absolute value of x minus 5 equals 9. You've already done that. You've already noodled through that. If we want to make the connection to the earlier part of our lesson, break it out of jail. X minus 5 equals 9. and x minus 5 equals negative 9. Add 5 to both sides. Add 5 to both sides. That's the algebraic solution. We've just reconfirmed our thought process up here. If we solve the equation absolute value of 2x plus 4 equals 14, remember to do that algebraically. To break it out, we have two equations. Both of these need to be set as equations to solve this. Subtract 4 from both sides, divide by 2, subtract 4 from both sides, divide by 2. Both of those are the solutions for that. So hopefully you've seen the connection between setting y equal to 0, x-intercepts, and solutions, making that connection between the graphing and the algebra. Alright, let's talk a little bit about above the axis and below the axis. Instead of just talking about where it crosses the axis, we're going to talk about where it is above the axis and below the axis. So let's go ahead and graph this so we can get a picture. Let's go back to down 3 and graph our upward facing V. And show how that goes like this. Where does it cross? We can pull that right off. We can see that it crosses at 1, 0 and negative 5, 0. Now let's think about this. Using inequality notation, how would you just represent the phrase all numbers greater than 1? How would you do that with inequality notation? That would be x's are greater than 1, right? And how would you write the inequality all numbers less than negative 5? You would say x is less than negative 5, right? So let's make a connection between these two inequalities and our answers to the intercepts. So let's look at the graph. Let's look at these inequalities. And what can we say about when x is greater than 1 and less than negative 5? What does that say? What is happening when x is greater than 1 or when x is less than negative 5? Hopefully you thought in your head, well, that's basically the portions of the graph above the x-axis, right? These represent the portions of the graph that lie above the x-axis. Remember how we can write this? They kind of go off in two different directions. When x is less than negative 5 or x is greater than 1, you've got a graph above the x-axis. Let's see this in the other direction. Let's talk about an and. For our final example today, let's graph our graph. So we go right 3, down 5. We're an upward facing V. So let's graph that and see where it crosses. Where does it cross? It crosses at negative 2, 0 and 8, 0. Let's think again about inequality notations. How do you talk about numbers that are less than 8? How do you write that in inequality? X is less than 8. How do you represent numbers that are greater than negative 2? We say x is greater than negative 2. So let's look at the graph for a second and see what that's talking about. When x is less than 8, greater than negative 2, what portion of the graph are we talking about? We're talking about the portion underneath, right? If we were talking about all of this happening at once, instead of an OR statement, how do we represent the numbers that are between -2 and 8? Between -2 and 8. This portion of the graph is everything between these two intercepts. So that means we are less than 8, and at the same time, we are greater than -2, right? What does this remind us of? This is our AND situation, right? Our less than AND. So if we are less than the x-axis, we're between these 2 points. So to make this connection here, let's finalize this for our notes. These values of x represent the portion of the graph below the x-axis. So this here represents the values of x, the portion of the graph that is below the x-axis, less than the x-axis. All right? Hopefully that helped bring you into the visual as well as the algebra. We'll continue with more graphics next time. Go ahead and try your independent practice for today.